Welcome to the Explainer. Today, we're going to investigate a really common programming trap, one where the most obvious go-to solution is actually the wrong one. Let's dive right in. We're digging into a classic algorithmic problem, where the approach that feels the most intuitive, the one that probably pops into your head first, it actually leads you straight into a pitfall. It's a fantastic case study in knowing not just what your tools can do, but maybe more importantly, what they can't do. So let's set the scene with our mystery. On the surface, it's a pretty simple problem statement, but it's hiding a really subtle complexity. Okay, here's the goal. We need to find every single substring that meets this very specific rule. And notice the wording, not at least k times, not at most k times, but exactly k times for every character inside that substring. We're going to use this simple string to investigate A, B, B, C. Our k is 2. So we're hunting for any substring where every character in it appears exactly twice. Seems straightforward enough, right? And here's our target. This is the ground truth. We know for a fact we are looking for 6, count them, 6 specific substrings. You've got the simple ones like AA and BB, but also the combined ones like ABB, where both A and B show up twice. 6 is our magic number. Let's see if our first suspect can find them all. Now, if you're thinking about this problem, your brain probably screams sliding window. It's our first and most obvious suspect. I mean, it's a fantastic technique for substring problems, so let's put it to the test. So, here's how the window moves. It expands from the left, grabbing characters one by one. It finds AA. Yep, that's valid. It keeps expanding, finds ABB. Also valid. It goes all the way to the end and finds aabbcc. Perfect. But what happens now? Once it's got the whole string, what if we try to shrink it from the left to find other substrings? Well, the condition immediately breaks. And that's it. The sliding window approach finds exactly 3 valid substrings. And, well, that's where our problem begins.
Wait a minute. 3 is definitely not 6. This is the plot twist. Let's dig into the analysis and see exactly where our suspect's story just completely falls apart.
This is the exact moment the alibi crumbles. The algorithm finished, totally confident in its result, but it's only telling half the story. So where are the other 3 solutions? This slide just lays out the evidence perfectly. Because the window started at the very beginning and only expanded, it could only find substrings that were anchored to the start. It completely missed BB, CC, and BBC, all of them perfectly valid but totally hidden from its narrow linear view. And this is the root cause. The problem has what's called a non-monotone property. In simple terms, just because a large window is valid doesn't mean a smaller piece of it is also valid. When our window expands from AAB to AABC, the condition breaks, and a simple sliding window can only shrink one character at a time from the left. It can't just intelligently jump ahead to find the next valid starting point. It's basically trapped by its own linear movement. Okay, so if our first suspect is out, we need a more clever detective, one that doesn't just look at what's in front of it, but remembers everything it's seen before. Enter prefix hashing. This right here is the philosophical shift we need. Unlike the sliding window, which kind of has amnesia, prefix hashing remembers every single state it has ever encountered. And this history, that's the key to finding all those substrings we missed. Now, this table shows the absolute magic of prefix hashing. Here's how it works. For each character we process, we keep a running count of A's, B's, and C's. The prefix state is a snapshot of those counts, but with a twist. We only care if the count is a multiple of our k, which is 2, so we do a mod k. A state of 0, 0, 0 just means we've seen an even number of A's, B's, and C's so far. And here's the brilliant part. Every single time we return to a state we've seen before, it means the characters between those 2 points must have balanced out to perfect multiples of k. Look at that last row. When we hit the final C, our state becomes 0, 0, 0 for the 4th time. This matches the 3 previous times we saw it, and that instantly reveals 3 valid substrings, AA, BBC, BBC, and CC. It uses its memory of the entire history to crack the case wide open. So, what's the key lesson here? How do you avoid this trap when you face a similar kind of problem out in the wild?
So here's the crucial takeaway, the rule of thumb you need to remember. If a problem's property is monotone, where if a big window is valid, any smaller window inside it is also valid, then the sliding window is absolutely your go-to tool. But if the property depends on an exact count across the whole substring, you need the power and the memory of prefix hashing to track its entire history.
And that's the thought I really want to leave you with. Where else have you seen these sneaky non-monotone traps? Think about problems like finding subarrays that sum to a specific target value, or maybe properties related to parity. Spotting the trap before you start coding is the real key. That's all for this explainer. Thanks for diving in.